we have a circuit with one battery and a second battery. We have resistor 1 and we have resistor 2. Let's say the EMF of the first battery is 12 volts, the EMF of the second battery is 8.0 volts. The resistance of the first resistor is 4.0 ohms, and the resistance of the second resistor is 6.0 ohms. At this point, we don't really have a way to solve this problem. In order to solve this problem, we need something called Kirchhoff's rules. Yes, there are. Kirchhoff's rules. The problem here is that we have two resistors. Are they in parallel? No. Are they in series?
No.
No. Okay. So, in order to solve that, we need Kirchhoff's rules. If you recall, I threw up a series of resistors before where we couldn't identify anything being in parallel or in series. In order to solve that, you would need Kirchhoff's rules, which is what we're going to go through today. The first of Kirchhoff's rules is the potential difference around a loop is equal to 0. There are two of Kirchhoff's rules. We'll do the first one right now. I'll do the second rule in just a little bit. Now, a loop. This is the simplest circuit diagram that we're going to do. It only has one loop. What's that?
Sounds like a microwave.
Yeah. We'll go with microwave. The potential difference around this loop is equal to 0. In other words, when we start here and we end back here, the potential difference around that loop is going to be 0, right? Because the potential difference between the 2 points that are the same is going to be 0. Makes sense. So we can look at this and we can say the EMF of this battery is 12, the EMF of this battery is 8 volts. So in this situation, you can clearly see that this battery is more powerful than this one. Therefore, the current is going to be going this direction. Current's going to be going through this direction. In other words, the current is actually going to go through the EMF, the battery 2. So this is actually a situation where we would be charging the second battery, because the first battery would be providing enough current. The current would be going the opposite direction through the battery, therefore it would be charging it. Our goal here is to find the current in this circuit. So what we do is we walk our way around the loop. The potential difference around the loop is equal to 0. Well, that's equal to, if we start here and we go this way across the battery. Now, this short terminal is Tyler positive or negative? Negative. This is negative, and this other one is positive. In other words, as you go this way through the battery, you go through the potential difference goes up, right? You go from negative to positive. Therefore, we're going to have a positive EMF across battery 1. Then we're going to go across resistor 2. Well, we have the potential difference across resistor 2. The potential difference across resistor 2. Now, as we go across a battery across a resistor in the direction of the current, what happens to the potential difference? Jenkins. Okay. This is something you need to understand. If you go across a battery, across a resistor, the second time I said that, across the resistor, what happens to the electric potential energy in that resistor? What happens to the charges? We lose electric potential energy. It becomes heat, sound, light, just depends on what kind of resistor it is. So if the electric potential energy is going to go down, then the electric potential difference is also going to decrease. So if we go in the direction of the current, the electric potential difference is going to go down. So we have a negative potential difference across resistor 2. Now we're going to continue going in the direction of the loop. We're going to go now across battery 2. Now EMF 2, does the potential go up or down as we go in the direction of the loop across EMF 2? Glenn. Actually goes down. Okay. Again, we have positive and negative. Do you see as we go from positive to negative that EMF is actually going to go down? We have a potential drop across this battery. And again, we have the potential difference across resistor. Actually this was resistor 1. This was resistor 1. This is resistor 2. And again, we're going in the same direction as the current across resistor 2, so we have, again, a potential drop across resistor 2. So 0 equals the EMF across 1. Well, what is the equation for the potential difference in terms of current and resistance? Zach?
The difference equals current times resistance.
It simply equals the current times the resistance. So this is equal to the current times resistance 1 minus EMF 2 minus the current times resistance 2. So we can now plug in numbers. 0 is equal to EMF 1 was 12 minus the current resistance 1 was 4 minus EMF 2, which was 8 volts, minus the current, which we're trying to find, times resistance 2, which was 6. So let's see, 0 equals 4 minus 10 times the current. So 10 times the current equals 4, so the current equals 4/10, or with sig fig, 0.40 amps. Just a very basic example of using one of Kirchhoff's rules to figure out the current in this circuit. As I said, this is the easiest circuit we're going to work with. Let's go through a more complicated circuit. Oh. Thank you. You're welcome. Here we have a battery, a resistor, a second battery, and another resistor, and another resistor. This is going to be, let's see, this is going to be a 10-volt battery. This is going to be a 1 ohm, 1.0 ohm resistor. This is going to be a 20.0 volt battery. This is a 2.0 ohm resistor, and this is a 3.0 ohm resistor. How many loops are in this circuit? How many loops in this circuit? Hadra?
2.
There are 3. Initially, you would see what I'll call loop A and loop B. Where is loop C, the third loop? Jenkins?
It's around the whole thing.
Around the whole thing. So there is a third loop all the way around the outside. So notice this actually has 3 loops. The second of Kirchhoff's rules is that the current into and out of a junction is the same. This particular point right here is a junction. I'm going to label that as point A, and I'm going to label this as junction B. So we have 2 junctions, junction A and junction B. So the current going into that junction is going to be equal, the net current going into that junction is going to be equal to the net current coming out of that junction. You always have, with the exception of this very basic one more loop than you need and one more junction than you need, and I'll walk through that when we go through this example. So when you're using Kirchhoff's rules, you do 2 things at the beginning. You pick loop directions, which I've done right here, and you pick current directions. So I'll go through and I'll pick some current directions. Let's assume that the current I1 is going in that direction. Notice then, what direction would the current be going through this 2 ohm resistor, please, Catherine? I'm sorry, that way is toward the left. Notice, if the current is going up through this resistor, it's going to be going all the way through what is called a branch right here. this branch is going to be going left here, up here, and to the right through this part of the branch. Let's assume as well that this 20-volt battery has a current and that it's going in the direction of the battery. I'll call that current 2. And then let's assume current 3 is down through this 3 ohm resistor. So let's start with Kirchhoff's second rule here. We know, let's look at junction A. The net current going into is equal to the net current going out of that junction. So what currents, yes, Nick?
How do you figure out where the currents are going?
You guess.
Yes.
That is a good question. You do your best, you look at it. What I've said here is we have a 20-volt battery here, a 10-volt battery here. In general, we try to get the charges to go through the battery from the negative to the positive, right? So generally that's the way the current would go. So if both of these batteries are working that way, then we would end up with this. I'll go through an example where we actually guessed wrong. We'll talk about what happens there, just to make sure you understand, because you will guess wrong, and that's okay. Yes, Matt?
I don't understand how you make the loops. Why does it start on the middle battery? Why can't it start on the left?
Okay, this loop here goes all the way, B goes all the way around this circle right here. Loop A goes all the way around this circle, and loop C goes all the way around the outside. It doesn't matter where it starts.
It's not starting.
The loop can start anywhere. It doesn't matter exactly where it starts as long as it goes through one single path, if you will.
All right.
And you said you had to pick loop directions.
Yes.
Why couldn't they go the other way?
Again, I'm picking
Okay.
loop directions. Right, exactly.
It's just a guess.
I just picked random loop directions.
But that could be wrong.
Yes. Well, actually, no, I'm sorry. The loop directions can't be wrong. The current directions can. The loop direction is pretty much irrelevant. I'm going to go through what it means with the loop direction. We're slowly building and understanding what this all means, and clearly that's not happy for you, but we'll get there, right? So I picked the loop and current directions. The next example that we do, you're going to pick them, and you're going to tell me why you're picking them in various directions. Gary, okay?
Yeah, okay.
All right. All right, so when we look at junction A, the current going into junction A, what currents are going into junction A? So
I2 and I1.
current 1 plus current 2 equals, what are the currents going out of junction A? Vlad.
Well, we have the current from the 20-volt battery.
Well, that's going into. I'm looking for the currents going out of junction A. Zach?
I3.
Current 3. That's the only current going out of that junction. If we instead look at junction B, the net current going into is equal to the net current going out of that junction. What currents are going into junction B? Sid? Current 3. What currents are going out of junction B? Hunter?
1 and 2.
Do you see how we have one more junction than we need? It's identical. It doesn't matter which one we pick, we end up with the exact same equation, right? Current 1 plus current 2 is equal to current 3. So that is the equation we're going to get for a junction. Let's go through the potential difference across a loop. Let's do the potential difference across loop A. Let's just start with that. We know it adds up to 0. Where would you like to start? Please walk through the potential difference across loop A. Sierra.
We have the potential difference of the battery, which is at the
So I'll call that battery 20. We don't have a name for it, so I'll just call it battery 20. Okay.
and then we're going
Is that positive or negative?
positive.
Why is it positive? Why is this positive here, Potterell?
It goes from the negative side of the negative to the positive.
As we go in the direction of the loop, which is this direction through the battery, we go from the negative to the positive. Therefore, that is a potential electric potential increase. Okay, keep going. So that's positive. Electric potential difference. Then what's the next one?
The 3 ohm resistor.
Okay, so the electric potential difference across the 3 ohm resistor, is that going to be positive or negative?
Negative.
negative? Why is it a potential drop across that resistor?
Because we're losing potential electric energy.
As we go in the direction of the current, that electric potential energy is going to go down, so we have a negative here. So 0 equals the EMF across 20 minus, we have the current times resistor for the potential difference across resistor 3. Well, that is then current 3 times resistance 3. So 0 equals 20 minus current 3 times resistance 3, which was just 3. So the current is equal to 20 over 3 amps. Okay, so 20 over 3, doesn't really matter, we just leave it as that. So that is the current through resistor 3. Okay, just for fun, what if we had picked the loop direction the other direction? Jenkins, how would this have changed our equation?
It would have been negative.
Just the negative of this equation, but it's the exact same thing, right? So the loop direction really is irrelevant. You're going to end up with the exact same equation. Generally, I try to pick loop directions so that they make a little more sense to me. This one makes more sense just because we have a positive potential difference across the battery, which is generally the way one likes it. So now let's do the potential difference across loop B. That's also going to be equal to 0. The potential difference around loop B. Please walk me through that one. Doorstep.
I have no idea.
Try.
Like, I wasn't here for the whole E thing, so I don't know what that is.
Ah, the whole E thing. Zach, what's the E thing?
It's the potential difference of a battery.
The potential difference of a battery, but it's close. It is the potential difference across a battery, but we need to understand what kind it is. What does E stand for, Winter?
It's the ideal potential.
It is the ideal potential, but that's not what it stands for. I agree that's what it is, but what is the E? Not Nick, you answered last time. Oh, wait.
Electromotive force?
Electromotive force, EMF. The E is the ideal potential difference, as opposed to what is the non-ideal potential difference across the battery. Hillary. The non-ideal potential difference across the battery, Travis? The terminal voltage, which would be the potential difference across that you actually see at the terminals. So when we just put the E thing there, that's just the potential difference across the battery. We're just saying it's an ideal battery. Well, what is it that makes a battery non-ideal, so that you don't actually get the potential difference, the ideal potential difference across it? Meg?
Internal resistance.
Every battery has internal resistance, which decreases the potential difference across the battery. Dorstetter, we're still on you.
Oh, okay.
Potential difference across, we're going around loop B.
Okay. So, we do
The E thing, what does the E thing stand for, Sierra?
Oh, electromotive force.
We could call it the EMF. So EMF,
Yeah.
EMF 20, positive or negative? Positive. As we go in the direction of the loop, we go from the negative to the positive, that electric potential goes up. Good. Keep going. What's the next one? As we go around the loop. All right, let's help her out. Tim.
Negative electric potential difference. Resistor.
Miller.
Positive,
Why should it be positive?
because it's opposite the direction of current.
If you're going in the direction of the current, the electric potential difference goes down. But our loop is going opposite the direction of the current. Therefore, this electric potential difference is actually going to go up.
How does that make sense?
I'll stop. Okay, I'll go through that again. If the current is going up through this resistor and we go in that direction, the electric potential difference is going to go down, right? We've already determined this because the electric potential energy goes to heat and sound and light and all those things. Which means if you're going the opposite direction, then the electric potential is going to go up. Where does that energy come from? It's not about where does the energy come from. It just has to do with what you're talking about, positive and negative. It's just multiplying through by a negative or multiplying through by a positive. It has nothing to do with whether the energy is coming from anywhere. It just has to do with the direction that we chose our loop in. That's it. Good. Next. The next one after the resistor 1, we have what? Mohit.
We have E of 10. It's negative
Why is it negative?
because direction you're going in.
As we go from the positive to the negative across the battery, the electric potential goes down. Good. The next one is resistor 2. We have the electric potential difference across resistor 2. Is that positive or negative, Sarah Jane?
Positive,
Why?
because it's going the opposite direction of the current.
Opposite the direction of the current, so the electric potential difference is going to go up. Bill. Michael, sorry. Sorry, Bill.
Wait, so wouldn't E20 be going from positive to negative also?
But, okay, notice, as we go across battery 20, we're going from negative to positive. As we go across 10, we go from positive to negative. So from negative to positive is an increase in potential, from positive to negative is a decrease in potential. So we have EMF of 20 plus current. Now you have to be careful here. This is current 1 times resistance 1. Current 1 times resistance 1 minus EMF of 10 plus this is current 1 times resistance 2. You have to be very careful here to keep track of which current and resistor you're talking about. So we then have 0 equals 20 plus current 1. We've got is what we're solving for. Current 1, resistance 1 was just 1 minus EMF of 10, which is 10, plus current 1 times resistance 2, which was 2. So we have 0 equals 10 plus 3 times current 1. In other words, current 1 is equal to negative 10/3 amps. What does that mean? Jenkins.
You made our loop the wrong direction.
No, it does not mean we made our loop the wrong direction. Because the direction of the loop, remember, is irrelevant, actually, in the long run. Hamza.
Our current flowing the wrong way?
The current is going the wrong way. We thought that the current was, that this battery was going to push the little charges, the little positive charges that don't actually move, up through resistor 1. But in the end, we were incorrect. This is, again, a situation where we would be charging battery 10 volts. Now, we have the incorrect direction. We got a negative. That's fine. We're just going to go through all the way to figure out each one of these currents. Current 1, current 2, and current 3. And we're going to keep the fact that we have the wrong direction. We'll show you how to deal with that. So now, we have, we've actually figured out, now we can figure out current 3. How are we going to figure out current 3? Zach? Just go back to the rules we had for the junctions. We know current 1 plus current 2 is equal to current 3. So current 3 then is going to be equal to negative 10/3 plus 20/3.
No, 20/3 is current 3.
I'm sorry, I get the wrong one. Okay, fair enough. I apologize. So we have then, we're solving for current 2. Current 2 is equal to current 3 minus current 1. Current 3 was 20/3 minus our current 1. Now, we are, of course, going to leave that negative in there because all the equations we got here were based on the diagram that we picked here. So what we end up with is 30/3 or 10 amps. So our answer is current 1 is equal to 10/3 amps, and current 1 is going to be down through resistor 1. Current 2 is equal to 10 amps, and that was up through EMF 20, and current 3 was equal to 20/3 amps, and current 3 was down through resistor 3. Now, we have this extra loop. So, the extra loop we can use to check our answer. So what is the potential difference around loop C? That's equal to 0. work me through the potential difference around loop C. John.
So we can start with the 10-volt battery, which,
We can start wherever you want.
okay, so, the 10-volt battery.
Positive or
That's gonna
negative?
be negative. And then you can, add the, resistance of the 2 ohm,
Potential difference
Potential
across
difference,
resistor 2. Why do we add?
because it's going the other way from the current.
The loop is going the opposite direction from the current. Good.
Yeah. And then you can add the potential difference from resistor 3. And then you can add the potential difference from resistor 1.
So 0 equals negative EMF of 10 plus each one of these is going to be current times resistance. We just need to get the right ones. So we have the current for resistor 2 is going to be current 1 times resistor 2. The current for resistor 3 here is going to be current 3, resistor 3. And then for the first resistor here, that's going to be current 1 times resistance 1. So 0 equals negative 10 plus current 1 was negative 10/3 amps times resistor 2, which is 2, plus current 3, which was 20 over 3 times resistance 3, which is 3, plus current 1, which was the 10 over 3 multiplied by 1. Second?
Negative 10 is.
Both of them. Okay. Thank you. What do we get? What do we get? 0 equals 0, right? It should work out. We know the potential difference around the whole loop should add up to 0. And therefore, this is a way to check to make sure that you have the right answer. It is not a 100% way guarantee that you got the right answer, but it's a good way of checking.